we are discussing a very important topic in antennas, what is called antenna arrays. First we saw some broad characteristics of a 2-element array, and later we started investigating what is called a uniform linear array. So, we saw in the last lecture that we have a uniform array which are excited with equal amplitudes. The spacing between adjacent element is also same, and then we have essentially 3 parameters for this array: the total number of elements in the array, the inter element spacing which we denote by d, and a progressive phase shift, that is the phase shift between the 2 adjacent element, that is delta. And we started investigating the characteristics of this array and the effect of these 3 parameters on the radiation pattern of the array. We define this quantity, the total phase, what is called psi, which is beta d into cosine of phi, where phi is the angle measured from the axis of the array. So, axis is the line joining the antenna elements, and the angle phi is measured from this axis. So, the angle psi is defined as beta d cosine of phi, which is the space phase, and an electrical phase which is in the excitation of the currents of different elements. So, that is the progressive phase shift delta. Then by simply applying the superposition, we get the radiation pattern of the linear array of n elements, and a normalized radiation pattern essentially is given by this expression. And then we investigated the properties of this radiation pattern, that is the direction in which the radiation is maximum, and we saw that when psi is equal to 0, that time all radiation terms add and we get a maximum radiation. So, the psi equal to 0 corresponds to maximum radiation. And then we also investigated the directions of the nulls, that is when the numerator goes to 0, that means when n psi by 2 is equal to 0, that time or 0 or multiples of pi, that time we get the nulls in the radiation pattern. Following further now, we would like to know what are the directions of the side lobes, what is the level of the side lobe, and also we will try to investigate what is the directivity of this array, and we will also try to see how the directivity changes as the direction of the maximum radiation changes. So, if I look at this function here, the numerator function, if I plot as a function of psi, if n is large, then this function is a rapidly varying function, this function is relatively slowly varying function. So, if I plot these 2 functions on the same scale as a function of psi, the function's numerator and denominator would look like that. So, here we are plotting the numerator modulus of that, and here we are plotting the denominator, and we vary the psi from 0 to 2 pi. So, this function is rapidly varying function if n is large, and wherever this function goes maximum, that time we have a local maxima. When this function goes to 0, we have null. So, essentially these directions where this function is maximum correspond to the directions of the side lobes. So, going back to the expression, then one can say that whenever this quantity n psi by 2 is maximum, and that will be when this quantity is 1, because maximum value of sine is 1. So, whenever this quantity is odd multiples of pi by 2, that time we will have a maximum for this function, and then we will have a side lobe at that location. So, today we see the directions of the side lobes. And this side lobe essentially comes in the direction when n psi by 2 is odd multiples of pi by 2. So, this is plus minus m plus 1 upon 2 to pi. Now, substituting for psi, which is beta d into cosine of the phi minus cosine of phi maximum, we essentially get now the directions for the side lobes. So, we can get from here this gives essentially the psi which is equal to beta d into cosine of phi, and let us call these directions as SL representing the side lobes minus cosine of phi maximum, that is equal to plus minus m plus 1 upon 2 into pi, and I can bring this thing 2 up there. So, this is to 2 upon n. Now, the direction of the side lobe by inverting this thing bringing beta d on this side, essentially we can write down now the directions of the side lobes. If I take n equal to 1, that is the first side lobe, then that will be giving me the level of the first side lobe after the main beam, and as I increase the value of m, essentially I get the amplitudes of the various side lobes. So, from here I can invert this relation. So, from here we get cosine of phi SL, that is equal to cosine of phi max plus minus m plus 1 upon 2 into pi 2 upon n divided by beta d, and beta d is 2 pi upon lambda into d. So, 2 pi would cancel, and we get from here cosine of phi max plus minus m plus 1 upon 2 into lambda upon d into n. So, now again, since this is representing cosine of phi L, we have to choose those values of m for which this quantity, magnitude of this quantity will be less than 1, and that essentially will represent the direction of the side lobes. One can also argue from the simple thing as we discussed earlier, that is finding out the local maximum requires differentiation of the expression, whereas if you follow a simple logic that there is a maximum between the two zeros of the function, we can very easily calculate the directions of the nulls by equating the function to 0. So, first we find out the directions of the nulls, and then we say somewhere halfway between the two nulls there must be maximum for the function. So, approximately we can calculate the direction halfway between the two nulls. So, if you are interested in finding out the approximate directions for the side lobes, then essentially we find out the directions of the nulls, and we say there is a side lobe between any two adjacent nulls, and halfway is the maximum for the local function. So, basically you have a side lobe which is halfway between the two nulls. So, by using any of the arguments, essentially we can find out approximately the directions of the side lobes. What is important, however, for the side lobe is not the direction, but what is the amplitude of the side lobe, because that tells you how much energy is leaked in the direction in which we never intended to send the energy. The array is supposed to send the energy in the direction of maximum radiation, that is what is called the main beam of the antenna. However, because of side lobes the power leaks, and that essentially is a wastage of power. So, more important parameter for the side lobe is what is the amplitude of the side lobe compared to the main lobe. So, in the normalized radiation pattern, as we know, the main lobe will have an amplitude which is 1, because when psi is equal to 0 this quantity would be equal to 1. So, we have the maximum amplitude in the radiation pattern, which is equal to unity. Then one can ask, what is the amplitude of the side lobe, or what is the amplitude of the highest side lobe? So, first let us say if I vary the value of this m from 1, 2, 3 and so on, how the amplitude of the side lobes will vary. So, as we said earlier, whenever this quantity is pi by 2, I get the first side lobe. Whenever this quantity is 3 pi by 2, I get second side lobe, 5 pi by 2 third side lobe and so on. So, essentially when we put the quantity here m, which goes from 1, 2, 3 and so on, the m equal to 1 would correspond to the first side lobe. Remember here the side lobe is going to come only after first 0 is crossed. So, m equal to 0 would not represent a side lobe, the m has to start from 1, because the first null will occur corresponding to m equal to 0, that will correspond to the this quantity when we put equal to 0. So, essentially what we find from this expression is that if I substitute m equal to 1, which corresponds to the first side lobe, then at that location this quantity will be 1 and sign will be essentially corresponding to n psi by 2 equal to 3 lambda upon dn. So, we get from here that for the first side lobe we have n psi by 2 that is equal to 3 pi by 2. So, you can get from here psi by 2 equal to 3 pi upon 2n. So, the amplitude of the first side lobe will be equal to, if I substitute the psi by 2 is equal to 3 pi upon 2n, that will be equal to 1 upon n mod of 1 upon sine of 3 pi upon 2n. Note here at the side lobe the numerator is maximum, which is equal to 1. So, we have substituted the value of psi corresponding to making this quantity 3 pi by 2 or this quantity is equal to 1. So, this is the amplitude of the first side lobe. Now, if I consider an array which is large, that means n is large, this thing can be approximated by sin theta equal to theta. So, this approximately I can say this is equal to 1 upon n into mod of 1 upon 3 pi upon 2n. The n would cancel and this approximately will give me 2 upon 3 pi. So, the amplitude of the first side lobe is 2 upon 3 pi. If I go to the second side lobe, that would correspond to this angle which is 5 pi by 2. So, n psi by 2, if I take 5 pi by 2, that will give me the second side lobe. If I take that equal to 7 pi by 2, that will give me third side lobe and so on. So, I have here the second side lobe amplitude which is approximately 2 upon 5 pi. The third side lobe amplitude will be approximately 2 upon 7 pi and so on. So, as I go away from the main beam, the m increases and the amplitude of the side lobe decreases. So, the highest side lobe essentially is the one which is the first side lobe which is next to the main beam. So, if I look at the radiation pattern, if I plot this radiation pattern now, the radiation pattern essentially will look like that in the Cartesian coordinate. Let us say this is the plot of this expression, the radiation pattern which we have got, which is sin n psi by 2 upon sin psi by 2 as a function of psi. If I put the function of psi, this is the one which corresponds to psi equal to 0, which we call as the main beam. And these are the locations of the nulls where the function goes to 0. So, these are nulls, and these are the locations of the side lobes. So, we have this is side lobe 1, this is also side lobe 1, this is side lobe 2, and so on. So, as we saw, this amplitude here is 2 upon 3 pi, this amplitude will be 2 upon 5 pi. So, the amplitude of this side lobe is reducing as we go away from the main beam. So, the highest side lobe is this one which is having an amplitude which is 2 upon 3 pi, which is approximately about 21%. So, this quantity first side lobe which we get is approximately 21% of the main beam amplitude. So, this is about, if I say this is normalized, so this is 1, this will be minus 0.21. This amplitude which corresponds to second side lobe which is 2 upon 5 pi will be about 13% of the maximum. So, this value will be 0.13 and so on. The same pattern if I put in the polar plot, it will look, there will be a maximum beam which corresponds to the main beam. Then we have a side lobe which is 21% of this, so which is like that, like this. Then there will be second side lobe and so on. So, this is the direction which corresponds to the main beam which is psi equal to 0. So, if I see on a polar plot, if this gives you unity, this will correspond to the 21% of the level which is first side lobe. So, the interesting thing which we note from this is the level of side lobe is not dependent of any of the array parameters. For example, we had 3 array parameters which were identified, that is the number of elements in the array, the progressive phase shift of the array, and the inter-element spacing of the array. The progressive phase shift decided the direction of the maximum radiation. The number of elements were not coming into picture in the direction of the maximum radiation. The nulls are of course decided by the number of elements in the array, and larger the value of n, more will be the nulls. So, the number of side lobes which you will see in the radiation pattern, they will increase when the number of elements increase in the array, but the amplitude of the side lobe is independent of number of elements. As long as n is large, the first side lobe which will be about 21%, and by no means you can really control these parameters. That means, for a uniform array you will always have the directions in which the power will leak, and the power will be leaking in the direction which will be substantial, because this will be about 21%, this will be 13%. If I sum up all together, you will see there is a substantial loss of power in the directions which are the side lobe directions compared to the main beam direction. So, side lobe as such is a very undesirable characteristic of radiation pattern, because that essentially represent the loss of power in the radiation pattern. However, for uniform array we cannot do much as long as the current distribution is uniform. That means if the currents are equally excited and if there is only progressive phase shift, we will always get a side lobe level which is 21%. The next thing then one would like to find out is what is the effective angular sector in which the radiation is going for this array, and that parameter, that thing we measured by a parameter what is called the half power beam width of the array. So, once the radiation pattern is given to you, the next interest would be what is the half power width of this radiation pattern. So, as we defined earlier, we have the radiation pattern. Let me draw the radiation pattern a little expanded. Let us say this was the radiation pattern as a function of psi. This is the direction of the maximum radiation, and if I take the 3 dB points of this radiation pattern, that is when the electric field goes to 1 over root 2 of its maximum. So, if I take these 2 points where this is 1 upon root 2, we can find these 2 directions, and this width, angular width, would give me the half power beam width. So, I can get first the half power beam width in psi, and then from there I can convert that half power beam width into the physical angle which is phi. However, in this case again we have to take the radiation pattern, equate the radiation pattern to 1 over root 2, solve the expression and then find out the directions. From there we can calculate the half power beam width. So, essentially what we are saying is, if I take this expression for electric field E, which is sine of n psi by 2 divided by n sine psi by 2, and equate that to 1 over root 2. Solve numerically this, because this we cannot solve analytically. So, solve this numerically, find out these 2 directions where the amplitude will reduce to 1 over root 2 of its maximum value, and then find out the half power beam width. However, this process is very tedious because this problem you have to solve numerically. So, what normally people do, they say if the array is large, if the number of elements are large, this function is almost like linearly varying from 1 to 0 up to the first nulls. So, if you make that approximation, this function is more or less linearly varying from here to here. Essentially, this width, the width between the first nulls around the maximum radiation, that will be approximately double of the half power beam width if this function is approximated by a linear function. And finding this direction of null is much easier than finding this direction where the function reduces to 1 over root 2 of its maximum value. So, for an approximate calculation of the half power beam width, what we can do, we can find out the directions of the nulls. From there we can find out the beam width between the first nulls, and then we say the half power beam width is approximately half of the beam width between the first nulls. So, we essentially say that approximately the half power beam width is equal to beam width between first nulls divided by 2. So, now if I have a radiation pattern, my job is essentially to find out the directions of the nulls. From there I can calculate the beam width between the first nulls, and then half of that would be approximately the half power beam width. However, it should be kept in mind that depending upon the direction of the maximum radiation, the 2 nulls may not be always visible. What do I mean by that? Let us consider a radiation pattern. Let us say this is the axis of the array and the direction of maximum radiation is somewhere here. This is my phi max. Now the radiation pattern might look like that. Other possibility, if the direction of maximum radiation is somewhere there, let us say this is the direction of maximum radiation. I may have a radiation pattern which will look like that. Since the radiation pattern is a figure of revolution around the axis of the array, essentially we get this will be, if I draw that, it will look like that. The same will happen here, like this. So since the range of phi is from 0 to pi, the nulls for this one, this radiation pattern which corresponds to this is visible, but the null corresponding on the other side of the main beam is not visible in this case. So now if I look at the expression for the side lobes which we have got from here, we get this quantity plus minus. So if I take the value plus here, it represents essentially the angle, the nulls which are on this side of the main beam, whereas if I take the negative sign, then that would correspond to the null which are on this side of the main beam. So in this case you will have a null corresponding to m equal to plus 1 and so on, whereas in this case the null corresponding to m equal to plus 1 is not visible, but the null corresponding to m equal to minus 1 is visible, that minus sign. The same is true in this case, that in this case the negative sign, null corresponding to negative sign is not visible, but the null corresponding to positive sign is visible. So in this situation one can make further approximation and can say that assume that the nulls are symmetrically placed in phi domain also, they are symmetrically placed in psi, and as we mentioned earlier there is a nonlinear relation between phi and psi. So the nulls need not be equispaced in phi. However, if we make an approximation that nulls are equispaced in phi, then we can essentially find out the direction of the maximum radiation and the null, which is half of the beam width between the first nulls, which is approximately equal to the half power beam width of the array. So for approximate calculation of the half power beam width of the array, we can now do this kind of simplification. So essentially what we do, we find out the direction of the maximum radiation, find the direction of any of the nulls which is visible, find the difference between these two directions, that is approximately equal to the half power beam width of the array. So ideally speaking, if these two angles are phi 2, let us say this is phi 2 and phi 1, and let us say this one corresponds to the null for which the angle is given as phi n 1 plus is the corresponding to the positive sign, and this angle corresponds to phi n 1 with negative sign. So the phi half power beam width phi is equal to phi 2 minus phi 1, that is the half power beam width, that is approximately, as we said, is phi n 1 plus minus phi n 1 minus upon 2, phi n 1 plus minus phi n 1 minus divided by 2, and that we said if the direction of the maximum radiation is phi max, that we said is approximately equal to phi n 1 plus minus phi max, and that is approximately also equal to phi max minus phi n 1 minus. So if I consider any nulls, so in this case this would correspond to phi n1 minus, this would correspond to phi n1 plus. So, this angle is approximately equal to the half power beam width. The same is true here, this angle corresponds to the half power beam width. So, if I have a situation like this, I will say half power beam width is phi n plus, phi n1 plus minus phi max. If I have a situation like this, then I can say this is phi max minus phi n1 minus. If both the nulls are visible, then I can calculate these two directions, and phi n1 minus plus minus phi n1 minus divided by 2, that will give me approximately the half power beam width. Let us take one of the cases. Let us consider that I use this expression. I have a situation something like this, and that gives me approximately direction of the half power beam width. So, let us say I use this expression which says the half power beam width is approximately equal to phi n1 plus minus phi max. Now, the phi n1 plus would correspond to, when this m, this, if you take this plus sign and this is m is equal to 1. So, by doing this we get the phi n1 plus, that would be equal to cosine of phi max minus lambda upon dn, cosine of this. So, we can get from here cosine of phi n1 plus minus cosine of phi max, that is equal to lambda d by n. We can take this sign as positive sign. We can expand this, the cosine, using the identity. So, this one we can get as 2 times sine of phi n1 plus minus phi max divided by 2 sine of phi n1 plus phi max divided by 2, that is equal to lambda upon dn. Now, this quantity, as we said, is nothing but the half power beam width. So, I can substitute now for phi n plus 1 as the half power beam width plus phi max. So, this one can be written as 2 times sine of phi half power beam width divided by 2 sine of, if I substitute for this, which is phi max plus phi half power beam width, it will be 2 times phi max plus phi half power beam width divided by 2, that is equal to lambda upon dn. I can expand this thing to get 2 times sine of half power beam width upon 2 times the expansion of this, which is sine of phi max cos of phi half power beam width upon 2 plus cos of phi max into sine of phi half power beam width upon 2, that is equal to lambda upon dn. Now, if n is very large, the half power beam width is much smaller than 1, because the beam width between the first nulls is going to be very small. So, if I say that if n is much greater than 1 for a large array, this would mean that phi half power beam width is much less than 1 in radians. So, I can make the approximation that if this condition is satisfied, so we know that if x is much less than 1, then sin of x can be approximated by x, and cos of x would be approximately 1. So, I can substitute now into this. So, this quantity here, which is very small, so I can make this quantity is almost equal to 1, and this quantity is half power beam width divided by 2. So, we can write down this expression now approximately as 2 times sine of, well, we are approximating this also by x. So, 2 times half power beam width upon 2 sine of phi max, this quantity is 1, plus cos phi max and this is equal to phi half power divided by 2. So, this is phi half power beam width by 2, that is equal to lambda upon dn. I can simplify this little further to get the expression which is phi half power beam width square cosine of phi max plus 2 times sine of phi max phi half power beam width that is equal to lambda upon 2 lambda upon dn. So, note here the expression which we have got is from here. So, this quantity is phi of half power beam width multiplied with this, that will give me half phi square half power beam width multiplied by cosine of phi x. Second term will be 2 times sine of phi maximum multiplied by phi half power beam width, that is equal to 2 lambda upon dn. Now, we can take 2 extreme cases, that is when the beam is in the broadside direction and the beam is in the end phi direction. That means, when the phi max is 0, that is the end phi direction, or when the phi max is pi by 2, that is the broadside direction. First thing we would note that if I solve this equation for the phi half power beam width, the phi half power beam width essentially increases as we go from broadside direction to the end phi direction. So, if I numerically solve this for different values of phi max, essentially we will see that as the beam direction changes from the broadside to the end fire, the half power beam width of this array increases monotonically. So, if I take these 2 extreme cases, that when phi max is pi by 2, that is broadside direction, and if I take the case when phi max is 0, which is the end phi direction, essentially I will get these 2 extreme cases, and then one can say that systematically the beam width will be increasing from the broadside direction to the end phi direction. So, for broadside array, So, phi max is pi by 2. So, I can substitute here phi max equal to pi by 2. So, this will go to 0, this will be equal to 1. So, I get here from here the half power beam width for the broadside array, which is approximately equal to lambda upon dn. For the end fire array, the phi max is equal to 0, and then this quantity will be 0, this will be equal to 1. So, you will get phi half power beam width, that will be approximately equal to square root of 2 lambda upon dn. Now, for an n element array, since the inter element spacing is d, the length of the array is d into n minus 1. If n is very large, the d into n minus 1 can be approximated like d into n. So, this quantity dn essentially gives me the length of the array. So, approximately then I can say this is lambda divided by the length of the array. Same I can do here. So, this is square root of 2 lambda divided by length of the array. So, when the beam is in the broadside direction, the half power beam width is inversely proportional to the length of the array, or for given inter element spacing it is inversely proportional to the number of elements. So, number of elements essentially plays a role in deciding the angular zone in which effectively the energy goes. As the number of elements increase in the array for a given inter element spacing, the half power beam width will become smaller, and consequently now the radiation will be going into a narrower zone, angular zone, or in other words the antenna array now has more focused radiation. The radiation does not go in larger sector, it goes into a very narrow cone. So, we get more focusing of the radiation in given direction, or in other words it increases directivity of the antenna when the number of elements in the antenna increase for a given inter element spacing. Or if I go in general, if I combine d and n together, I can say that as the length of the array increases, which could be a combination of the inter element spacing and the number of elements, in general the directivity of the antenna would increase because the half power beam width of the antenna would decrease. So, around the broadside direction, since there is the inverse relation between the half power beam width and the length of the array, the antenna beams broadens almost linearly as a function of length. However, as I go towards the end fire direction, then the dependence is weaker because we are having a square root of the length of the array. So, essentially as we go from for a given array, two things we have to observe now. One is that I scan the beam for the phased array, let us say this is the array, I will get the narrowest beam in this direction and I will get the broadest beam in this direction. So, the beam width essentially increases as we change the direction of the beam from the broadside to the end fire. This is very important because whenever we use the antenna array in an environment where we want to scan the beam by changing electronically the phases, what is called the phased array antennas, the beam width does not remain constant while scanning the antenna. So, purpose of the phased array antenna is that without moving physically the antennas, if we can control electronically the phases, or if I change the progressive phase shift of the antenna array, then the direction of the maximum radiation would change and the beam would scan something like that, from maybe from horizon to horizon, depending upon how much phase gradient you are going to put on the array. While doing this, however, we do not want the beam shape to be changed significantly, but we see here that will not happen. When we have a beam in this direction, you will get the beam width which is narrowest. When the beam comes here, it will be broader compared to this, and when beam comes to the horizon, the beam will be the broadest beam. Visualize this radiation pattern as the beam is scanning in the 3 dimension, and in fact they have a totally different appearances. It looks like, if I consider the planar radiation pattern, it will look, the beam width will be narrow here, something like that. When it comes here, it will be broader, so it will look something like this. Similarly, when it comes on the other side, it will look broader like that. So, it looks as if the beam simply is broadening, otherwise the pattern practically remains the same. That is the appearance you get from the planar radiation pattern. However, as we mentioned earlier, you should always look at the radiation pattern which is in 3 dimension. So, if I do that, then it is radiation pattern is figure of revolution around the axis of the array. So, for a broadside, the array would essentially look like that, which is more like a disk, something like this. Whereas when I go to the end fire array, the end fire array will be figure of revolution around the axis, so it will be like that. So, in one case, though the beam in the planar looks only change in shape or change in the half power beam width, if I visualize the radiation pattern in 3 dimension, the radiation patterns are quite different in the 2 situations. The end fire will look more like a balloon like that, whereas the end fire or the broadside would look more like a flat disk, which is figure of revolution in this direction. Having understood this, then one can go to calculation of the directivity of these antennas in the 2 extreme cases, which is the broadside and the end fire direction. And then we will get something surprising, because looking at this, it appears that when the beam is scanning from here to here, since the beam is broadening, the directivity of the antenna is decreasing, because the half power beam width increases. However, this conclusion may be erroneous if we make only on the basis of planar radiation pattern. So, further we will investigate the directivity of uniform array, and that understand we will develop essentially by getting the 3 dimensional radiation pattern of this array.